Let's get started. Today we are honored to have Miruna from the University of Cambridge. Miruna is a PhD student working with Pietro Leo in Cambridge, and she's going to talk about generative modeling for synthesizable small molecule design today. And let's get started.
Yeah, thanks for the introduction. I'll be talking about generative modeling for synthesizable small molecule generation. So the plan for the talk is that we'll first look into GFlow nets, and I'll give a short intro into GFlow nets, and followed by an introduction to small molecule generation. And then I'll introduce SynFlowNet, which is a GFlow net for synthesizable small molecule generation. And then we'll talk about Outlook. So first, GFlowNets, the goal for GFlowNets is that given a reward function, we want to sample compositional objects sequentially, such that the probability of sampling the objects is proportional to their reward. So that is, when I'm saying compositional objects, this can mean any kind of object which can be constructed through a sequence of decisions or actions, such as graphs, and they can take the form of molecules as well, or sequences, etc. And the way we do that is that we train a generative policy that satisfies a flow matching criterion, which is different from flow matching in the sense of flow matching models, and I'll go into it in a little bit. But really, the hypothesis for GFlow nets and the starting point here is that a good objective is to generate objects X proportional to their reward. And this is what the GFlow nets are trying to achieve. Now, the way I like to think about GFlow nets is that they are RL, reinforcement learning, but with a slightly different training objective. And that is because they share a lot of commonalities. They are both defined by a state and an action space, a reward function. We're trying to learn a policy that samples actions given a state, and they are defined by transition dynamics, etc. But the distinction is, again, that in RL, we're usually trying to find the maximum reward, and we can introduce things like entropy there, but this is usually the goal. And for GFlow nets, we want to find all the modes of the reward function. Now, how are GFlow nets trained? Again, we go back to this constraint of flow matching, which takes the form of inflow into a state equals to outflow. So to concretize the intuition there, I'm showing this toy example with a directed acyclic graph where we start from an initial state and we transition through various states to get to terminal states, to which we assign a reward. And again, if we remember that the goal is to sample these terminal states with probability proportional to their rewards R, the way in which the GFlow achieves that is that it defines this flow quantity, which is really something that approximates the probability of being into a state or transitioning from a state to another. And it approximates the float quantity through this flow matching criterion. So here in this highlighted case, the way a valid solution for the flow quantities is one that achieves that for example, for S1. Now, the more modern ways of training GFlow nets have departed from modeling flows to modeling policies. So here I'm showing a trajectory balance loss, which is the default loss used in training GFlow nets. And we will see that it first defines a forward policy function, which defines the probability or the distribution over the children of a state, the children of a node in one such graph, as well as a backward policy, which is sort of a novel component for GFlow nets, which also defines the probability to transition to parents of a state. And the intuition here is that we want the two policies to match. We want the forward flow in a network to be balanced by the backward flow. And through this loss formulation, we also approximated partition function, which you can think about as the total flow quantity in the network. So this F equal 10 here, the sum of all of the rewards in the terminal states. And we also define a reward. Now, the backward policy, it can be set to uniform, it can be set to a constant, or it can be learnable via the trajectory balance loss or in different ways, which is something that we also played around and I'll talk about later. Because the spoiler here is that it can be used to incorporate additional constraints in the network if we choose to train it separately from the forward policy. So to sort of recap, a G-fluent is defined by a point directing the cyclic graph with unique source and sink states, a reward function that computes rewards for terminal states, and the flow parameterization theta such that if theta approximates the flow or unnormalized probability of being in a state. And we also need to define a state and an action space such that the actions are used to transition from one state to the next. And here is where we can be creative about the design of the space and design of the MDP. Going back to why we chose G-fluenets to model things like molecules, we can go back to this hypothesis that we started from, that a good objective is to generate objects and sample them with probability proportional to their reward. And what comes out of this sort of for free is diversity, right? Because we're not biased towards sampling objects that we get through multiple trajectories and such. And this is especially important in biology and chemistry, where the models that we use to approximate things that we care about, things like properties of molecules or affinities of molecules to other molecules, are fundamentally imprecise, right? We have this trade-off between cost and accuracy of models, of calling a model. So in this sort of scenario, it's better to cast a wide net. So in this example here, we'd rather try all four modes rather than oversampling from one mode, because it's very likely that some of the modes are incorrect because of the specification of the reward function being incorrect. So now going into small molecule generation, unless there's questions, also please feel free to stop me at any point. Why do we want to generate small molecules? Well, the answer is that we want them to bind to protein targets. And this is very relevant in early stages of drug discovery, where let's say that one has identified a target, so a protein responsible for a disease pathway, and we want to generate a small molecule that inhibits that protein. And then we move on to further stages in the drug discovery pipeline. Traditionally, this is being done via virtual screening, where we start from huge combinatorial virtual libraries built from reactions and building blocks, and we start filtering out molecules based on things that we define, such as drug likeness, how similar these molecules are to other drugs, how similar they are to some structures that we know are good and potent, physicochemical properties, and so on. Now, the sizes of these libraries scale exponentially, and it becomes really unfeasible to be able to screen all these libraries with high fidelity models. And we would also want to leave this search paradigm and be able to sample molecules such that they belong to a distribution that we know is good for binding to proteins, for example. So we naturally ask, can we use generative modeling instead? Now, how the community usually goes about designing small molecules is that we ask the question of what to make. And here, again, we search or we sample from a huge space, which is approximated to be somewhere 10 to the 60 drug-like molecules. And then we ask the question of how to make that molecule. And what I want to convince you is that we can, and actually we should be answering these questions jointly instead of sequentially. So to go into motivation for that, I'm going to show some examples of molecules sampled from generative models for small molecules, where indeed we've left these libraries of predefined molecular compounds, but the models might have become a little bit too creative in that these molecules are not molecules that one can either synthesize in a lab or that are physically plausible with many clashes and energetically unfavorable positions. Of course, these are exaggerations, and models can do much better than this, but it's just to prove the point. And because there's even more subtle examples where these two molecules, you'll have to take my word for it, that the molecule on the left-hand side is synthesizable, whereas the one on the right-hand side is not synthesizable. So the two are very similar, right? But it's unless there is a sequence of reaction pathways leading to these molecules, we cannot synthesize it. And even things like heuristic scores with these two being quite similar to each other cannot distinguish between the two. So then going back to the drawing board, we can think about molecule generation and molecule design and remind ourselves that there are several choices of action space, ranging from most expressive to most constrained. So we can design molecules at an atom level where we define nodes as atoms and edges as bonds, and we join them together in things like junction trees or in a molecular graph. We can design molecules at the fragment-based level where we fragment drug-like molecules into these uh, subgraphs and then join them together. Or we can define and design molecules from chemical reactions. And although the latter is the most constrained one, we can argue that we can still tap into quite a large chemical space with only reaction-based molecule construction. So here, what we've done is an experiment which approximates the size of the state spaces. So the size of the spaces that we have access to, the chemical spaces that we have access to, with ranging numbers of building blocks of molecules that you react together. And we see that with something like 200,000 blocks, I'll talk about what enamine is a little bit later, we can access a space as large as 10 to the 16 molecules, which is pretty large to start with. And if we do design models that scale even better, then we can tap into even larger spaces. So we're choosing this reaction-based formulation for our GFlowNet action space. So the way SynFlowNet works is that we define this MDP from as I said, chemical reactions. So we start from S0, the initial state, which is an empty molecular state. And the first action is always to populate it with a building block. What a building block is a molecule that is readily available, it's synthesizable, we can buy it and react it in the lab easily. And then the way we transition from a state to the next is using a chemical reaction. So we can construct our molecular graph via these very highly constrained transformations, which are chemical reactions, such that at the very end of this DAG, we end up with a molecule for which we compute a reward. In this case, what we've done in SimFlowNet is it's a reward that approximates binding affinity to a protein target, but it can be other things such as models for toxicity or chemical properties. Now, the way in which we define these reactions is for something called templates, which can be unimolecular or bimolecular. This means there's a molecule to which we do a transformation, or there's a molecule to which we add another molecule and then do the transformation. And these templates, what they are is that they map the rearrangement of the atoms, where the atoms from the reactant end up in the product. The policy is parameterized using a graph transformer. So we have in each of these states, we embed the molecule using a graph transformer to which we add separate MLP heads for different action types. So we have action types for adding a reactant, for unimolecular reactions, bimolecular reactions, and then very importantly for adding a second reactant to our block. And this is quite important because we want to be able to scale to 200,000 molecules. So that means essentially our policy outputting 200,000 logits. And then we can easily think about how this can run into scaling issues, right? So we play around a little bit with this with the policy here, where instead of just doing naive sampling through softmax over the logits that the policy outputs, what we do instead is we realize that the action space from which we're sampling is organized in a chemically biased way, right? So we have building blocks, which are molecules, and they can be more similar or less similar to each other. And this chemical space organization can help us scale the sampling better. So what we do is we take the MLP outputs and the dot product of those with binary Morgan fingerprints, which are some way, it's a binary vector for encoding molecules based on substructures occurring into that molecule. And then we obtain logits and sample from there. Now, I was talking about the backward policy in the beginning, and I want to draw attention that this sort of reaction-based MDP comes with a lot of caveats. So when we define the backward policy, we want to ensure that the parents of a state are actually valid parents. What that means in a reaction-based setting is that we want to obtain parents. We want the policy uh, to define distribution only over valid parents, and that is parents of nodes that make it back to a building block. So this finite set of 200,000 molecules that we can actually purchase. What that means essentially is that when we have our state here um, that does not lead to a building block, our policy should not be sampling it. It should be masked. So the default choice of using a uniform backward policy where we give equal probability to the parents of these states is not ideal in this case. So what we do instead is we train the backward policy to make it back to the original state. One can realize that you have such training data for the backward policy from the forward policy. So that is, we have annotations of how a building block can go into and grow into a larger molecule, and we can use maximum likelihood to train over that data, or reinforce, where we teach the policy to make it back to S0 by giving a positive reward for ending up in a building block or a negative reward otherwise. And if you're familiar with chemistry, this is analogous to retrosynthesis. So this idea of having a big bulky molecule and decomposing it into building blocks in chemical reactions to figure out how to synthesize it. And we have some cool findings to show that this model that is, the purpose of the model is to train such that we obtain molecules with high rewards, high binding affinity to protein targets, can also tackle retrosynthesis through this backward policy formulation. So to talk about results now, the first choice was using a GFLONet over reinforcement learning. So here I'm comparing to 3 different reward functions and synFlowNet, so our GFlowNet formulation, and maximum entropy RL through soft Q-learning. And what we see is that the bottom plot shows how the through sampling, so from an untrained policy all the way to more iterations of training the policy, we're exploring more and more modes with synFlowNet compared to soft Q-learning. Here, I'm defining a mode as a Merkle scaffold, which means taking a molecule and stripping away all of the types of atoms and all of the functional groups from it until you end up with a molecule backbone, sort of. So we see that soft Q-learning collapses much earlier compared to synFlowNet, which explores many more modes compared to it. Now, in terms of how we defined our action space, I'm comparing here to a fragment-based GFlowNet. So one that, instead of using these chemical reactions transition from a state to the next, just merges fragments together. And also such a fragment GFlowNet that jointly optimizes for affinity and synthetic accessibility, which is a heuristic for how easy it is to synthesize a compound. And what we can see is that both in terms of reward and synthetic accessibility, synFlowNet is better in that it manages to create molecules that are actually synthesizable as claimed by this retrosynthesis software, with almost no cost and diversity. So these are some examples of how molecules look like when we use the fragment-based GFlowNet compared to a reaction-based GFlowNet. And this is much better in terms of synthesizability. Now, when we compare to reInvent, which is a staple for molecule generation, it's a very strong baseline, which is a likelihood-based model with a trained to optimize for different reward functions. Now, in this case, it's this proxy for affinity to a protein. And when we also compare against this Monte Carlo tree search method that also uses reactions, we see that we get a good balance in terms of high reward, high diversity, and good synthetic accessibility. And compared to reInvent, especially to which we are comparable in other metrics, we strike a better balance in terms of novelty and reward. So what that means is when we look at how similar the molecules that SimpliNet generates are to Campbell, which is a database of chemical drug-like compounds, we achieve a good trade-off in terms of high rewards and low similarity to known compounds compared to reInvent, which is very biased towards inheriting those chemical features from Campbell. In terms of scaling experiments, which remember it's very important because we want to be able to scale to libraries of really large reactions and starting materials or building blocks. I'm looking here at the performance of using the fingerprint bias compared to not using it. And we see that with fingerprints, we have much better training efficiency. And when we move along the axis of scaling to larger and larger action spaces, we preserve higher rewards compared to not using that bias of fingerprints. And we also utilize more building blocks. So the model explores more of the action space compared to when we don't use fingerprints. The backward policy, which I was mentioning, is sort of tapping into retrosynthesis. I'm looking here at the percentage of solved routes. So that means how many times did the backward policy manage to decompose this bulky terminal structure into its constituent building blocks. We see that with a uniform backward policy or with a free backward policy, which is just updated for the trajectory balance laws, the percentage of solved routes is much better when we train the backward policy separately. And for a test set where we take molecules outside of our training distribution, we see that the model does actually manage to perform retrosynthesis. And also because the two policies are interlinked through the trajectory balance laws, we also looked at the effect it has on the forward policy. And a reinforced backward policy seems to also promote the diversity that we obtain through the forward policy, which is a nice finding. And if we think about it, what happens, and the thing that we wanted to prevent with these backward policies, which we train separately, is that we don't want to lose flow or probability outside of the MDP. Yes, if we end up, if the policy assigns probability to a state that will not end up into a building block, that means sort of assigning probability outside of our MDP, because there's no action that in the forward policy pass would lead us, would account for that building block. And this is an example of a retrosynthesis pathway extracted from our model. And now finally, what's very exciting about SimpliNet is that it can be paired or it can be aided by this a parallel line of work where people are developing increasingly better binding affinity predictors. So in this case, the Boltz team has tied SimpliNet with their affinity predictor in Boltz-2. And they compared SimpliNet to traditional virtual screening. And we see that SimpliNet designs achieve a good values in terms of ab initio absolute binding free energy calculations. Now, going forward, what SimpliNet demonstrated is that given an oracle function or a reward function, we can design high-scoring molecules with good diversity, and we explore multiple modes of the reward distribution. And the other nice thing is that we can do so in a tailorable synthesis chemical space. And it's really relevant to drug discovery where in very early stages, you want to test things fast and fail fast, such that if you want to test designs that promote high binding affinity, SimpliNet can directly generate designs to which the vendors that one works with has access to. And that's quite nice. You can switch up the chemical reactions from Simplonet's action space to whatever reactions you have access to in a lab. Now, the drawbacks are that the model does not model 3D structure, which one can argue that is very important to drive interaction between protein pockets and small molecules, and is prone to reward hacking, right? Like this idea of we can only approximate binding affinities, and the model can always go outside of the distributions of those trained models. So we can start asking questions about, right, the going back to the drawing board, we want to learn the probability over molecules given a protein pocket. So if we hold on to this hypothesis that we must be able to model 3D structure in order to create binders to such protein pockets, then but also preserve synthesizability, then what do we do? And this is, I just wanted to give a short intro into some other line of work that I've been doing, which is called Syncogen. And it's a model that jointly generates reactions and coordinates. So what that means is that it's a joint discrete diffusion and continuous flow matching model where you start from a noise distribution and you evolve that into a coordinate distribution of molecules through continuous flow matching. And we define this building block graph that we put masks over, essentially, and then denoise from masks all the way to the identity of these building blocks masks. So we have these reaction-induced bonds, which we define as edges, and nodes, which are these differently colored blocks that we want to merge together. And this is a paper that's been recently accepted at iClear, and Andre and I are going to present in, I think, less than 2 weeks at another reading group. And yeah, if you have questions about it, let me know. So to conclude, it is really the case that atom-only models struggle to produce synthesizable molecules, and we can use synthesis-constrained models to, instead of enumerate and filter, which is the current paradigm in drug discovery, design molecules which are viable by design. Now, looking forward, synthesis-constrained models are trained on these custom enumerated data sets and cannot make use of this rich data source, which is protein ligand crystal structures. And there's exciting opportunities with people constructing such data sets. And there's always the question of how to scale to even larger reaction data sets and more complicated chemistries, and also the caveat that synthesis is hard. And we need to also account for things like yield or regio and chemicals, chemoselectivity in reactions, which is something that we don't currently do. But with that, thank you, and very happy to take questions.
Thank you, Miruna. Thank you for the talk. Is there any questions? Or maybe I will go with the first. So I'm wondering like how scalable or how expensive it is during the training phase, because for the training you are using the trajectory balance laws, and which
Mhm.
seems that you need to back probably through the generative trajectory. And if the trajectory is very long, then it means that your network will backprop for a lot of times. And it seems would it be very expensive in practice?
Yeah, the nice thing about reactions is that trajectories won't get very long, right? You don't really model pathways where you have trajectories that are more than 10 nodes. So it's already quite good in that sense.
Let's see.
Yeah, and then in terms of training, it's very reward dependent. That's what I've noted through me training Simplonet on different cases. But yeah, it's usually the case that you reach high rewards or your reward starts to plateau in around let's say 8 to 24 hours, depending on the reward again or on your action space.
I see. I see. Um, and can you also talk about the similarity between the SymphonNet and like diffusion models? Because if, for example, in diffusion, it is doing a generative process in in the same space, right? You don't have any like dimensionality increasing or decreasing in like in this SymphonNet case, because in this SymphonNet the dimensionality can be changing during your generation or during the this kind of the noising process because you're adding some building blocks or removing some building blocks.
Hmm.
Yeah,
Right.
yeah.
So you're talking about the
Okay.
dimensionality of the input to the policy function, right? That
Yeah.
changes. Um, I guess, yeah, you're right that there's that distinction there. In diffusion models, what you do is you have your input that gets padded, right? So at sampling time, you start from noise, and then that gets inputted into your backbone model, and then you essentially go from noise all the way to samples, but then the dimensionality of your input stays constant in that you always have a maximum length to which you're adding padding to your length. Um, yeah, that's right. I guess the thing is that you kind of create this flexible backbone model in SymflowNet that doesn't have a fixed sort of dimensionality in the input, and that works out. Unless I don't understand the question. Are you asking about the effect of that or?
Yeah, I'm just wondering like the similarity between these two
Mhm.
and kind of like for example in in diffusion model the noising process usually is fixed. But like in the SymflowNet is this kind of the noising process, this kind of the removing the building block is like learnable or it is fixed.
So in the forward policy, now there's two different processes, right? So you have the forward and the backward policy. And in the forward policy, you're essentially, what happens is you're just sampling based on on whatever embedding you have in your current state. You're sampling from your action space, and then you're adding a building block. Now, the backward policy is where the removal of the building block comes in, which I think, yeah, I get your analogy. Your kind of the backward process is the same as noise addition in diffusion. Um, and you get to like this absorbing state at the very beginning, which is an empty molecular state. And that's sort of the analogy and the similarities between the two. But the formulation of the two is quite different, right? Um, and it's also this distinction of, yeah, you can do it diffusion in discrete spaces, but especially in the case of G-flow nets, there's some work which does extend it to continuous spaces, but they do work best in the case of discrete spaces where what you do is as you said, you're just adding or removing an entire part of your molecule or sequence or whatever you're modeling.
Okay. Thank you.
I have a question. Do you hear me? Miruna?
Yeah, I can hear you.
It's Christian. I'm a biologist, so maybe my question is a bit naive. I'm using Boltz 2, and as I understood, since Boltz 2 defines the reward in your model, is there a risk that SymFlow net learns how to exploit the reward rather than discover real ligands?
Yeah, it's definitely a risk. It's one thing that also made me want to explore models that are not necessarily reward based. Because that's something that definitely happens, especially because the training distribution of bolts too can very easily be different from whatever distribution Symplonet acts in terms of chemical space. So it's definitely a very valid point. And there's things one can do to prevent it, such as introducing multi-objective optimization. So rather than just optimizing for and keeping bolts too as your reward function, you can do a composite reward function with something else that keeps the designs in some desired chemical space, for example, and you penalize going outside of the training distribution of bolts too, and other kinds of tricks like that. But yeah, it's definitely something that happens. Yeah, thanks for the questions.
All right. I guess there's no more questions today.